Hello? 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 Can people in the back hear me? Can people in the back? Okay, good. So somehow that display 2 doesn't work, but at least we have display 1. You can just all look at this way. Okay. So other presentation clear enough for you to read? The lighting? Okay, good. Unfortunately, somehow I tried to turn off the light in the first few rows, but it only allows me to do so much. So I hope if you cannot read the presentation, just feel free to come to front rows. We have plenty of seats in the front. Okay. So we're gonna continue of what we have left in last week. So I mean, since it's been a few days, I like to do a quick review before we go ahead with what we're going to talk about today. So in our last lecture, we basically started to talk about mode balance, and the whole idea is to basically figure out in our interested system, it could be a reactor, it could be anything. How do we know if we draw a control volume? How do we know the amount of species in that control volume change with time, right? And conceptually, in such a control volume, amount of species that are present in this control volume, and it's accumulation, we call it, right? It's how it changes with time. We call it accumulation. This comes from 2 parts. One is if there's fluid motion, then there will be some species being carried into this control volume, right? And if they are diffusion, which is something we're going to talk about today, then there will also be some species being carried into the control volume. So the second source is generation. If we have some reactions taking place in this control volume, then we'll have a change in the amount of species that are present in this control volume. So mathematically, okay, we can write it down as this equation where we have basically 3 terms. On the left-hand side, we have the accumulation term, right? Where basically we know the concentration of species I at the space at any time, and then we can do an integral of the species concentration over the control volume that gives us the total amount of species in this control volume. Then we take a derivative that tells us how fast it changed, right? That tells us the accumulation. On the right-hand side, the first term is let flow, right? So we have this is a flux vector, and we take the dot product of the flux vector with the A is the unit normal vector at a particular ds location. And this dot product gave us the net flow, net outward flow through this ds. Then we take an integral over the whole surface of the control volume that gave us the total outward flow, right? Then we assign it a minus sign that just changed outward flow to netward flow. Then that's net inflow. Okay, then we have the reaction term. Similarly, this is a production rate. Then we do the integral over the whole control volume. That gives us the how much species are being generated in this control volume, right? So this is a mathematical equation. And then once we have this mathematical equation, we can apply it to any problem we are interested in. So the first example we talk about is tank filling and emptying. And in this example, we know the inlet flow rate and the inlet concentration of species I. And we know the initial concentration I and height of the fluids in this tank, okay? And we made some assumption about homogeneous solution, no reaction, no volume change. Now the question asks us to solve number of moles of species I, that are present in this tank over time. Then what we did is we apply this mole balance equation, right? We first write down this equation. Then next thing is we need to, draw the control volume. So then we can simplify this equation, right? So in this case, we draw control volume, right? So actually, you can draw control volume like this. So it does not change with time. Then because upper space here is air, is nothing, so it can be neglected. Then basically for the accumulation term, so if you because in this case the control volume doesn't change with time, so it's time invariant. So that allow us to and also the concentration is constant, right? So it's in this whole mixture, it doesn't change with space. So that allow us to take the derivative operation into into this, and meanwhile we can further take C here, right? And that give us this, which is this, okay. Which is basically the amount of like moles in the liquid, and how it changed. And is the amount of moles in the liquid, and dNi dt tell us how fast it changed with time. The net flow term here, and this is kind of like equation. Then in this case, there are only two flow terms, right? We have the inlet flow, we have outlet flow. So then the total flow, let flow, is going to be the inlet minus the outlet, right? Very simple. Then because there's no reaction, this term is vanishes. Then we can just let these two terms equal to each other. So that gave us, this term equals to this term, right? Which is written here. Okay. Now we have one equation, right? Now we need to typically you do is when you write down an equation, you just inspect all the parameters that are present in this equation to see and to figure out which parameters are known and which parameters are unknown variables. So that gives us a sense about what to do next. Then what you do is basically inspect all the parameters. Ni is what we need to solve for. CI, V dot, they are already given in this problem. CI in, Vi in dot. And this CI is the concentration in the liquid mixture, which is unknown. And but it can be converted to Ni, right? Because CI is basically Ni divided by V. Okay. The V out can be computed by this equation, right? So it basically depends on it is dependent on the height of the liquid in the tank. Okay. So and here the volume of the liquid in the tank can also be related to heightness, to height, because the cross-sectional area of the tank is fixed. So that gives us divided by A C H. Okay. Okay. Then what we do is just plugging all these conversions into this equation and see what happens. Okay, so let's see. Right, so if you plug in all of them into here, you get one ordinary differential equation, right? That basically relates Ni, number of moles of species I in the tank, which is something we need to solve for. We need to solve. And this Ni is going to be I mean its changing rate, dNi dt, is going to be a function of a lot of like given parameters, CI in, VI in, AC, pi r squared, and 2G, right? These are all knowns, but also they are unknowns. One is Ni, right, which is itself, and then we have H, right? So obviously we cannot solve for two unknown variables with only one ordinary equations, right? So that's why we need to figure out another equation just to solve for H. And we know in this problem, H is basically the height of the liquid, and it has to do with the volume change. And we know the inlet flow rate is not necessarily the same as the outlet flow rate, right? So it's subject to change, and basically then we should be able to find out an equation to relate H with with other known variables by this equation, right? Which is kind of like the volume change of the liquid in the tank is going to be the difference between the inlet flow rate and outlet flow rate. If you do that, this is known, and this can be right. This can be connected to this, right? Then you do some conversion, right? V is basically, here, dV is this. And if you plug in all these relationships into the equation, you will get this, okay? Right? And this gives you another ordinary differential equation that relates, the derivative of H, which is like how the liquid height change with time, to be dependent on basically itself. Okay, all the other parameters are known. AC is known, V dot E is known, R is known. Okay, now we have the second differential equation, and put them together. We have two ordinary differential equations with two unknown variables, Ni and H, right? So in theory, we should be able to solve these ordinary differential equations for N and H over time, as long as we know the initial conditions, right? Because we are solving ordinary differential equations, and we need to know. You can do this for a simple problem. You can do this. That's not my computer. Somebody just hacked that monitor for somehow. So this is, we have two ordinary differential equations, and to solve them, we need to know the initial conditions, right? And once we know the initial conditions, right, we can either solve it for simple problems. We can solve it analytically. But for this problem, because we have a square root here, probably we're not going to be able to do it analytically. So but at least we should be able to do it numerically, okay? By basically approximate the derivative with difference, right? And this can be done in Python. There should be some like function for you to help you to do that, right? Now I think in the NumPy library, there should be some function to help you to do that. Okay, and if you don't know how to do that, you can come to Friday's office hour. Okay. Now, in this problem, we made some assumptions, right? Kind of very strong assumptions. For example, the solution is homogeneous. That means in the solution we mix the solution very well. So there's no concentration gradient whatsoever. Concentration does not dependent on space. It's always the same at any point in the liquid, in the solution. Then there's no reaction. Then there's no volume change on mixing. That means it's ideal solution. Okay, so that's why we can do this. We can derive these two ordinary differential equations quite easily. But what if the mixing was incomplete, right? If that's the case, what do we do? Any idea? So in this case, I mean, clearly we know CI, right?
You would just use
Well, actually, in this case, the problem becomes more complex. Yeah. So when we have this homogeneous homogeneous solution assumption, CI, right? That's the concentration of species I in this volume, in this tank. It's only a function of time. It changes with time, but it does not change with space. But now, if we do not have very well mixing, that means CI is not only so slow, not only a function of time, it's also a function of space, right? Now I'm using X for space here, right? Which means, you know, when we made an assumption, so let's go back a little bit. So we can just, okay. So here, remember, we just, we simplify this equation greatly because we made some assumption. One of the assumption here is CI does not change with D, right? But now if it does not change with V, if C is like if C is dependent on V, then we need to find a way to link, you know, how C is dependent on V. Right? Makes sense? Okay, the second assumption we made is there's no reaction inside, right? If there's reaction inside, then in the third, you know, in the more balanced equation, we have third terms, right? Accumulation equals net flow plus net reaction. If there's reaction present, then the net reaction term cannot be neglected. We have to figure out it. Okay. Then if there's the third assumption, if the mixing is non-ideal, right? That means there's volume change during mixing, then this is not necessarily correct, right? Because this assumption, the inherent assumption of this equation is the volume change of your liquid is purely dependent on how much liquid you take in and how much liquid goes out. Does not consider the mixing effect. Yes.
So with the first assumption, if mixing is not, we can't assume that there's ideal mixing. Is it possible to solve it by hand, or do you have to kind of software model?
So that's a good point, right? If mixing is not complete, then you are dealing with a problem. Concentration is going to be dependent on, it's going to be like a function of a three-dimensional space, right? X, Y, Z. Now, and this problem becomes too complicated for you to solve by hand, right? But conceptually, you can still, you know, do some conceptualization. But in the end, if you really want to solve it, you have to use computer. Okay. Okay, so in this case, let's come back to the third assumption, right? Then basically we have to consider volume change on mixing. Then we have to add like some additional term here, just to, you know, kind of like a just to basically modify the equation a bit to consider, you know, how much extra volume you get because of the mixing, right? That is, again, cannot be solved by hand, right? Unless you have a good model to consider, you know, when this inlet mixed with the existing solution here, what would be the volume change purely because of the mixing itself, not because, you know, you have some liquid leaving the tank. Okay. But again, I don't think we're going to deal with this in your homework problems, if you're gonna have to deal with them in your homework problems, then there will be conditions. Well, there will be some other conditions given so that you can just address this. Now, we solved for Ni, right, which is the total amount of moles of species I in the tank, and as well as the height of the liquid in the tank. But sometimes we don't care about total amount of moles in the tank. We only care about the concentration, right? Because, for example, we're going to use use this as a feedstock for a reactor, afterwards. So we don't care about what's inside this tank. What we care about is what we can get from this tank, right? Then here, what matters is the concentration, CI. Okay, how do we do this, right? Well, one thing we can do is, right, you can solve the Ni, then you solve for H, then you get CI is just, Ni divided by ACH, right? Right, that's seems to be a simplest way to do that. But I mean, maybe we don't have to solve these two equations at the first place. Maybe we have some easier way where we can just build a ordinary differential equation that relates CI with all the unknowns and itself. Okay. Okay. What we do is you can just break down Ni, in this ordinary differential equation. Ni is CI multiplied by V, right? And we know both CI and V change with time. So then we can just expand this full derivative into its two components, right? We have CI multiplied by dV dt. This is assuming CI is constant, plus VI multiplied by dCi dt. This is assuming V is constant, right? So this is like full derivative. So mathematically, we can do a bit simple review here. Mathematically, let's see. If we want to do the full derivative of a product of x, y, well, so then basically it equals x dy dt plus y dx dt, right? And plus, then there's a component called dy dx dt. And mathematically, this term is so small and it can be just neglected. Okay. So this is from your math. Now we have this, right? We kind of we link Ni, right, with Hi, with H, with C, right? So then if you have these two equations, you can just plug dNi, dHi into it, and then you can get an ordinary differential equation for dCi dt. Okay. And what we found out is dCi dt is this. Okay. And it's dependent on H and the CI. So again, then with these two equations, okay, with these two equations, you have two variables, H and CI, right? And you have two ordinary differential equations. Then that's how you can solve them directly. Okay, any questions? Okay. Great. So if no questions, we're going to move on to the next topic here. So we just talked about the mole balance in the integral form, and we discussed we gave one example to discuss how we can use that equation to solve real problems. Now we're going to talk about another form of the ball balance equation, which is the differential form. So this is the integral form, right? We have accumulation equals net flow plus net generation. So the whole idea here is we in our reactor or in our interested system, we draw a control volume, and we start from the accumulation in a small subset of this control volume in like a very small volume. Then we take integral over the whole volume. They give us the total, total amount of species in this control volume. And similarly, we can do the net flow across the whole surface, the total reaction across the whole volume, right? Now, but in a lot of cases, right, we don't really have to go to to kind of treat the whole control volume, right? Maybe it's more convenient if we only consider one point in our system, right? Then there's a way we can simplify our equation from the integral form to the differential form. And to do that, we have to apply the divergence theorem. This is a mathematical theorem that can correlate a this is like a surface integral into a volume, like the volume integral of a divergence term. Okay, so here the idea is, here we have a Q as a vector that's point out through a surface, right? Then when we in this case, this Q is our flux, right? Then in order to get the total, I mean the net flow of flux Q in our control volume, we do the integral over the whole surface, right? That divergence theorem told us we can compute the divergence of vector Q. Then we can compute the same thing by doing a volume integral instead of a surface integral, right? We can just integrate the divergence of vector Q over the whole volume. That will give us the same thing as the surface integral here, right? And what does the divergence mean? Conceptually, divergence means so the divergence vector operator is a vector, and a Q is a vector, and we know the dot product of two vectors gave us a scalar, right, which is a quantity. So conceptually, it means, let's see, it means just like a net outflow of this vector. Okay. For example, we gave three examples here. On the left example, we have the vector Q, and all of them pointing out, right? Now when we take the divergence of vector, sorry, this is vector V here. We take the divergence of vector V, it's going to be positive, because in this case, the net flow from this point, right, this origin of all of these vectors are positive, right, because they are going out, right? So basically, by definition, going out means divergence is positive. Okay. And in this case, in the example in the middle, right? So we have a series of vectors pointing toward the center of this point. Now we have net inflow. Then the divergence is gonna be negative. So in the third case, we have equal amount of vectors pointing up and pointing down. Then at any point, right? Any point, if you compute a divergence, it's going to be zero because amount of flux going up is going to be the amount of flux going down. So they're going to cancel each other. Okay, that's how we treat it conceptually. So mathematically, this is like the divergence operator, or it's also called gradient operator, right? So this is the operator. So it does not have like, does not have very physical meaning unless you apply this operator to a vector or to a scalar, right? So in the divergence, in this operation, right, if we do a dot product between this gradient operator and the unit vector, so because this is a vector and this is a vector, right? Q is a vector. And we know the dot product of two vectors mathematically means we just, in this case, we can decompose. We're talking about 3D space, so all of our vectors can be written in terms of like the three elemental directions, unit vectors in our 3D space, right? In this case, I, J, and K, right? Then dot product just means when we take the dot product of them, we just compute the product of them that give us this, right? Then we compute the product then that give us this, and similarly we can get the Z component. Then we add them together. Spoiler. Okay, so then that will give us a scalar, right? Okay, so now we can just so now we can just plug in this. We can apply the divergence theorem. We can convert this surface integral into a volume integral. That will give us this, right? So we just replace n here. We just replace q here with n, right? That gives us this. And because we have like the volume integral, we can just sum up these two volume integral together, right? Into the bracket. Then so now we have this, right? We have this equation. Now, if we assume volume is fixed in time, right? We can always do that because control volume is arbitrary and it's what we pick. And you can pick anything, and we can pick a control volume that's fixed in time. Then we can then V does not change with time. And because V is arbitrary, in order for this equation to hold, right? Remember, we can change V whatever we want. In order for this equation to hold, then the integrand must be equal, right? Then we can simplify this equation to this, right? This is so-called differential species small balance. Okay. Then a few notes here. If there's no reaction, SI is going to be 0. If this divergence term is positive, then dCi over dt is going to be negative. That means Ci is decreasing, right? What does it mean? That means, we can apply this equation to any point in this control volume, right? And if at that particular point, the divergence term is positive, right? That means we know that conceptually divergence means net outward flow. So if the net outward flow is positive, then the net inward flow is negative, right? In other words, if the net outward flow is positive, that means species I are leaving that point, then you will have less concentration at that point. That's why the concentration of C on the CI, its derivative is going to be negative, right? So that means it's decreasing. Okay. And similarly, right, if divergence of NI is negative, then this is positive, CI is increasing. If that's reacting, but if let's say at a steady state, the concentration does not change with time, then we have the divergence to be equal to reaction, right? That means physically this means whatever are being produced at that particular point, right, will leave that point so that the concentration remains not changing. Okay. Great. So that's the last slide of this lecture. Well, I guess we can stop here, and we will continue on Friday to talk about Fick's law.
Another question.
Yes.
You mentioned a little bit the molar flux, but we haven't really gone into that in detail.
Yeah. That's what we're going to talk about next lecture.
Okay, so right now with the differential